Okay, at the end of the last hour, which wasn't all that long ago, it was just yesterday, we spoke about three different situations: irreversible, reversible endothermic, and reversible exothermic reactions. And we noted what the equilibrium curves would look like. Blue is the equilibrium curve, which has the net rate equals 0. This was the direction of increasing rate. Again, equilibrium. These curves with the direction of increasing rate. And again, this direction is the direction of increasing rate. And we noted that in the best possible worlds, the easy thing to do, both irreversible and reversible endothermic reactions were fairly easy to design for, because we just wanted to maintain the system at the maximum possible temperature. Exactly how we do it, we'll discuss it in a little bit, but that's exactly what we wanted to do. Whereas the reversible exothermic system presented much more of a challenge. The reversible exothermic presented a challenge in that, since it's exothermic, wherever we start out, the temperature would like to rise because we're liberating heat upon reaction. But instead, we want to actually reduce the temperature as the reaction proceeds. So this is going to require some drastic intervention in order to get the temperature to follow this profile, whereas it wants to go off to the right. And clearly, at low conversion, we want to start at as high a temperature as possible, because at low conversion, where I have pure reactants, the higher the temperature, the faster the rate. But very quickly, once we reach the maximum of one of these curves, going any further would have us limited by equilibrium. So we want to move, as we saw last time, we want to move along the locus of maxima, of the constant rate curves. So that was, of course, all a little bit qualitative. So what we'd like to do is we'd like to do an enthalpy balance. In order to get a bit more quantitative. So what's the general equation of chemical engineering? What's the most general equation of chemical engineering?
Accumulation equals N minus output.
Slowly. I can write that fast. I know I can write fast, but not that fast.
Accumulation equals N.
The rate of accumulation is equal to
N minus out plus generation
minus
consumption.
consumption. Okay, so we're going to do a steady state mass balance. So in steady state, this is 0. So therefore I have 0, and I need to write what in and out is. So in, so I have H for the reactants, which I'm going to call H1. And that is going to be equal to, here what I'm going to do is I'm going to do this very simplified. Usually I use my CPs as per unit mass or per unit mole. These are going to be CP totals. This is total. So if you like, it's the M, it's got the M in it already, times the temperature minus the temperature of the inlet. Well, minus the reference temperature. So it's the temperature of the inlet minus the temperature of the reference. So this is again the total CP. Usually I would have an M here. H of the products would be H2, and that's going to be a CP2, again total, times T2 minus T0. And the consumption. Well, if we have a single reaction, so here I'm going to assume single reaction. And that's going to be delta HR, the heat of reaction, times XA. Now, notice I didn't make that as consumption, because when I have an endothermic reaction, this thing is positive. So delta HR is the amount of heat absorbed. So it's positive when I have absorption. Okay, so why don't we Now, we have some sort of reactor system, and I'm going to choose. Now, in addition, I also have heat addition as Q. So this is the heat that I add. And of course, if Q is negative, I'm subtracting. So this could be of either sign, and this could be of either sign. When delta H is positive, I have consumption. When delta H is negative, then the consumption is negative, or I'm producing heat. When Q is positive, I'm adding heat. When Q is negative, I'm taking heat out, I'm cooling. Okay, so why don't we write a balance here? Oh yeah, and I'm going to let the reference state be the inlet to the reactor. So here, this is sort of a black box, if you like, little enthalpy balance. This is just to give you a sense of what's going on. It's not really super precise. Okay, so let's plug in. So I have in. Well, if the inlet equals the reference, in T inlet is equal to T0. It's okay. It's okay, we started earlier than we said. To make up for all the times we start later than we said. Okay, so we have T inlet is equal to T0, so this just is 0. So in is 0 plus Q minus the out. Well, out, I've got, if I don't have complete conversion, then part of the reactants are at, part of the reaction mixture is still reactant, and part of the reaction mixture is still product. So the part that's product is I have CP2 T2 minus T0 times XA. That fraction has been converted. Plus CP1 times T2 minus T0 times 1 minus XA. Where here I'm assuming that the reactor is at temperature T2. The inlet is T0, the reactor is at temperature T2. Okay, so that's in minus out. And now in generation, I'm assuming is 0. I'm lumping generation and consumption together, where this is consumption, so I have to subtract off minus delta HR XA, and this thing is equal to 0. The accumulation at steady state. So what I'd like to do here, remember the goal. Why am I doing an enthalpy balance? Because if you remember, in the mass balance, I have a rate, and the rate is a function of XA and T. And in order to do the design equation, I need it only to be a function of XA. So what I would like to do, so this goes into the design equation. But when I have an isothermal system, then T is fixed, so it's not a problem. When I have a non-isothermal system, say adiabatic or non-adiabatic, then T can vary. And I would like to tie the variation in T to X so that I can write this as RA of XA, T of XA. In which case, it's just RA of XA, and I can go back to the design equation the way I had it before. So this particular thing here, T of XA, is coming from my enthalpy balance. So that's why I'm doing the enthalpy balance, because I want to get T of XA, XA of T, etc. Okay, so the first what I'm going to do is I'm going to solve for XA of T, and then I'll also solve for T of XA, we both do it. Okay, so this is 0 is equal to Q minus CP. So everything with an XA I'm going to keep on one side of the equation, and everything without an XA I'll keep on the other side of the equation. So let's move this to the other side. So I've got a CP2, T2 minus T0, XA. That's on the left. I move this to the left. This stays on the Q. Here I also have the XA over here. I also have plus delta HR. That's this term. I move it to the other side of the equation. The Q I've left on the right. And now I've got a CP1, T2 minus T0. That's the 1. And of course it's coming with a minus sign, because I have a minus sign out here. And now I have a minus, which is a plus, and then I move to the other side of the equation, I get a minus, CP1, T2 minus T0, XA. So I can solve for XA, if I haven't made any mistakes. XA is equal to Q minus CP1 T2 minus T0 divided by CP2 minus CP1 T2 minus T0 plus delta HR. And what I'm going to do is I'm going to multiply top and bottom by -1. If I do that, I have a plus here and a minus here, a minus here, and a minus here. Now let's just make sure this is the form that I want to get it into. Yeah, that's fine. Okay, so this is XA of T2. So my end will be done. XA of T2, where T2 is the temperature of the reactor. Here I'm assuming there's just one temperature for the reactor. And I'm looking at the outlet. Okay, so I'd like to do some interpretation. First, let's do an interpretation when Q is 0. If I don't add or subtract heat, then what is CP1 T2 minus T0? CP1 T2 minus T0 is the heat required to take the reactants and heat them up from the inlet temperature to the outlet temperature. So at CQ equals 0, this is the heat required to heat up reactants from T0 to T2. And how about this? This is the negative of delta HR plus C2, P2 minus CP1, T2 minus T0. And this delta HR is at T1. So I want you to notice that what is this? This is the heat of reaction at T1, the negative heat of reaction at T1, minus CP2 minus CP1 delta T, which is exactly, if you remember last time, the way I adjust delta HR from T, there is no T1, I'm sorry, this is T0. The way I adjust the heat of reaction from T0 to T2. So this is the heat of reaction, this whole thing is the negative heat of reaction at T2. Per unit reaction at T2. So this is the heat of reaction, which is the heat absorbed per unit reaction at T0. And this change, CP2 minus CP1, T2 minus T0, is how I move the heat of reaction from T0 to T2. So I have a very nice physical explanation of what XA, how XA depends on T from the heat balance. The extent of the fractional conversion of A is the heat required to heat the reactants from T0 to T2 divided by the heat of reaction. And this is an adiabatic, in an adiabatic sense, the heat of reaction at T2. Okay, well, why don't we look to see...
Question.
Yes?
You just said it's adiabatic, so why?
Q is 0. It's adiabatic. This interpretation is adiabatic at Q is equal to 0. Obviously, this equation is not adiabatic. At Q equals 0, this interpretation was. Clearly, this is not adiabatic because it has a Q. I assume that was your question.
Yeah.
So this, again, holds this interpretation only for Q equals 0. Obviously, for Q not equal to 0, it would be heat required to heat up the reactants from T0 plus T2 to T2 plus the amount of heat I add, divided by this. So, if you like, maybe in general I could say plus heat added. So this is the Q. Okay, well, just as we saw for X at T2, we did that, if for no other reason than to get this physical interpretation. To plug in here, I need T of XA. So let me just solve the other way. So to solve the other way, I'm going to again go back to this equation and keep everything that has a T2 in it, move that to the other side of the equation, and keep everything else on the right. So on the left, I'll have a CP2 XA plus CP1 1 minus XA. All of that times T2 minus T0. This term and CP1 1 minus XA, right, plus this. And I'll move everything else to the other side of the equation. So here I have delta HR XA minus Q. So I have that T2 is equal to T0 plus delta HR XA minus Q divided by CP2 minus CP1 XA. This minus this plus CP1. And I probably want to multiply again top and bottom by -1, but I'm just going to make sure I didn't make any mistakes. So I've got CP2 XA, this side equation, CP1 1 minus XA on this side of the equation. And then I've got on this side, I think I have the sign backwards. So these sign move to the left, so on the right I have Q minus. Yeah. Sign wrong. Q minus. That looks, I think that looks better. And let's just check to make sure. Yeah, that's correct. Okay, so okay, and what I'd like to notice here is that often CP of the products and CP of the reactants are not that different from each other. So if CP of the products and CP of the reactants is similar, then this thing just sort of looks like, so this is if CP1 is about equal to CP2. This is very similar to T0 plus minus delta HR over CP1 XA plus Q, XA plus Q over CP. Okay, why did I manipulate into this form? If you remember, well, so here I have T as a function, right? One thing you can see is that when CP2 and CP1 are similar, then the temperature, let's forget Q for a second. Well, actually, I can put Q here. If we forget Q for a second, then what we can see is that the temperature looks pretty much linear in XA. Let's go back to this equation, if we see that as well. So this equation, I have XA of T2 is equal to Q plus CP1 T2 minus T0 divided by minus delta HR at T0 minus CP2 minus CP1 times T2 minus T0. And again, if CP1 is about equal to CP2, sometimes it is, sometimes it isn't, then this is just equal to, I can forget this term, and I have CP1 over minus delta HR. Times T2 minus T0, CP1, plus Q over minus delta HR of T0. So what I'd like to do is I'd like to look at the case where Q is 0. So let's first look at the case. Yes?
Is the Q a constant?
Q is whatever we make Q. Q is up to us. Q is up to us. Depends how you do Q. If you have an electrical heater where you supply a fixed amount of current, then Q is a constant. It's just proportional to the current. But if Q is determined by, for example, removing insulation from the reactor, if it's getting too hot and you want to cool it, then Q is proportional to the temperature of the reactor minus the surrounding temperature. If the surrounding temperature is the same as the inlet temperature, then Q would be proportional to T2 minus T0. All depends what kind of heating and cooling you do. So the answer to your question is, it depends. Insufficient information, specification of the problem, so forth. So let's first look at if Q equals 0, adiabatic case. And what you can see is that XA of T2 in this limit is pretty close to a straight line. It's a constant times T2 plus a constant, minus a constant. And the reason I write that is because these curves are XA versus T. So we needed both. XA versus T are for the curves, that's this form. T versus XA is important because that's where I do my calculations. So let's just plot what's going on here. So if I look at XA versus T, and if this is T0, then what you can see here is that this looks like, if I forget about Q, and Q is equal to 0, it looks like essentially a straight line that goes from T0 and goes upward. And the slope here, if I have an exothermic reaction, delta H is negative, so minus delta H is positive, so I have a positive slope. And it's a little curve because delta H really does depend on T because Cp prime is not the same as Cp double prime. But this is for an exothermic. This is for an isothermal. Isothermal, delta H is 0, so the slope is infinite. And for an endothermic, it looks something like this. And let's see what happens, and I should have used colors, so let's use colors. Exothermic will make pink. You think of pink as hot, and blue as cold. An isothermal, I guess we can make green. Now, what happens if I now introduce Q? If I introduce Q, so if I heat up the reactor, then now let's say, what if Q is proportional to T2 minus T0? Now that would come if it were, again, as I just mentioned to Chad's question, if we take off insulation from the reactor and we let it just exchange heat with its surroundings. So in that case, Q would be, as you know from your unit ops class, UA delta T. So delta T, if the surrounding temperature is the same as the inlet temperature, so here I'm making assumptions, I'm making the surrounding temperature equal to the inlet temperature, then Q would be proportional to T2 minus T0. And what you would find is that Cp, now let's just make sure I have the signs right. So what happens is I would increase, I would have Cp1, did I do this right? Q plus Cp1, is that all, did I get the signs right here? No, it was minus Q. So it was minus Q. That makes more sense. No one's checking me here. Can't check if I make this. I've read mistakes. Okay, so what happens here? So for an exothermic reaction, when delta H is negative, then the slope gets smaller. The slope gets smaller, that means the curve moves this way. The slope gets smaller. So if Q is positive, then the slope moves that way. I still get a straight line because this is proportional to T2 minus T0 passing through here. I made it a little curvy because delta H really has a little variation. But what that says is I decrease the slope. If I decrease the slope, this moves over to the right. On the other hand, and that makes sense, it gets hotter faster. On the other hand, if it's endothermic, I'm on this side, if it's endothermic, then delta H is positive, this is a negative number, this is a positive number. So if I have a negative number, and I add a positive number to it, then what's happening? I'm decreasing the negative, I'm increasing the slope. So like I'm increasing the slope. So if I'm increasing the slope, then this curve moves in this direction. And similarly, if Q is negative, then everything goes in the opposite direction. What happens if I increase the inerts? Well, if I increase the inerts, I'm increasing the total CP, CP1. So increasing inerts, forget about Q right now, increasing inerts, if delta H is negative, if I have an exothermic reaction, increases the slope. So inerts increase the slope. And how about if I have, in the other case, well, delta H is positive. Well, delta H is positive, increasing inerts. So this is negative, so it becomes a larger negative number. So again, increasing inerts goes in this direction. So, and that makes sense. When I increase inerts, then it's harder to heat up the system. There's more inertia to the system because I've got all this extra stuff that sucks up the heat. So the system becomes more isothermal. I don't get as big swings in the temperature. Whereas when I add heat, then I shift everything and make the temperature higher for a given X. Obviously, if I subtract heat, it goes the opposite direction. If I subtract inerts, things become more extreme. Okay, so let's compare this. What's called? Hello? Hello? You're in a moment. Okay, so let's compare with the ideals that we have here about what we were thinking here.
Question?
Yeah.
I think I missed the point about the isothermal line. Could you say again how you explain the vertical line for the isothermal?
Yeah, if it's isothermal, then delta H is 0. Delta H is 0, I have an infinite slope. It's a straight line over.
I thought that that delta H, right, it was like just the stoichiometry coefficient on the entropy of the entropy of formation of the product and reactants. Is that the same delta H you're talking about here?
Delta H is the heat of reaction. It's the amount of heat
Right, so it's
absorbed
the
per
entropy
unit
of
reaction.
products minus the entropy of the.
It's the amount of heat absorbed per unit reaction, which is related to the enthalpy of the reactants and the products. You have an isothermal reaction, and the enthalpy of the products in the reaction is like the same. So therefore, the change is equal to 0. When I have an exothermic reaction, delta H is negative. When I have an endothermic reaction, delta H is positive. When I have an isothermal reaction, delta H is 0. Okay, so clearly, if I have an isothermal reaction, that would be perfect. That would give me the green line I want. Just by coincidence, it's a green line. But it's also, more importantly, it's vertical. If I have an endothermic reaction, then if the reaction is only slightly endothermic, and this moves slightly to the left, it's not quite what I want, but a slightly endothermic would be okay. If it's very endothermic, then what do I need to do to get it closer to my ideal? Add heat and or inerts. Inerts make it more vertical, and heat make it more vertical. So that's what I would want to do there. Yes?
So if the line is curved, does that give you like a certain range in which you want to keep your temperature for the system in?
Can you please explain the question?
Because, all right, as it's drawn, it's just a vertical line. So you
As
want
what,
to keep
as
your
I have many lines on the blackboard. You have to tell me which
all
one
right,
you're
for
talking
the
about.
reversible endothermic.
Yeah,
We
this
just
is a
have
qualitative figure. I mean, this is not quantitative, it's qualitative. So you're talking about the desired line? The
Yeah.
green?
So if it's curved, then what is your desired temperature? If the line is a little bit
If
slanted?
what is curved?
You said the line becomes a little bit slanted.
Wait a second, the line. I said, which
the
line?
T-max line. The vertical T-max line.
One thing at a time. this is the ideal of what we would like. This is, ideally, we want a straight line. When we look at the heat balance, this is the heat balance, plot of the heat balance. The heat balance says if we do nothing else, the curves are going to go either to the left, if it's endothermic, to the right, if it's exothermic, straight up if it's isothermal. Because this comes directly from this equation, which is the heat balance. Delta HR, in order to get a perfect straight line, delta HR would have to be independent of temperature. Delta HR really has temperature dependence. So since it has a slight temperature, usually it's a slight temperature dependence. So therefore these lines won't be completely straight. Will they curve this way or that way? That all depends on the details of the reaction. I just wanted to illustrate here that it's not going to be perfect. It may not be perfectly straight. But that's the heat balance line. The goal is the goal. The goal, we would like it to be straight. Now, if we get something that's curved, if the actual line looks like this, well, we still want to get it closer to the vertical, because that's our goal. Any other questions?
I might be jumping the gun a little bit, but isn't this saying then that we can't do anything for the exothermic because it's always going to go to the right, and we can't go?
That's the next question. This is perfect audience plan. Exactly what I was going to get to next. Okay, so let's address your question. What happens when we get to the reversible exothermic? If we get to the reversible exothermic, if we do nothing, what's going to happen to the temperature? It's going to follow the pink line. It's going to go off over here. What are the consequences of it moving off over here? Less conversion, yeah, because you don't, you're limited by the equilibrium. What other consequences? That's consequence number one. What's that?
You go past your Tmax.
So you're likely to wreck something in the reactor. And what's the consequence to your job? Unemployment line. Okay. So obviously we don't want to do that. Now there are a few things we can do. One thing we can do is instead of starting here, we can start over here. So if it gets hotter, it's not so bad. The problem is, as it gets hotter, it's more limited by the equilibrium line. Moreover, if you start here, the rate is much, much slower than if you start here. So that's not a really good strategy. It keeps the reactor from blowing up, but it doesn't necessarily keep you off the unemployment line. So what would I like to do? Well, what I need to do is, one thing is I can add inerts. So that'll keep it from going over here and might keep it from wrecking the equipment. But that still doesn't cure the problem of the equilibrium limitations. So then what I also want to do is, instead of Q plus, what I want to do? Q minus. I want to take heat out. I want to cool it down. And if I cool it down, I not only make it more vertical, but if I take enough heat out, I can turn it over and have it decrease the temperature. So here I want very drastic cooling. And with very drastic cooling, I don't want to have inerts. Because inerts will mean I'll have to cool even more, have even bigger cooling load to cool down the inerts. Cooling, inerts make things more vertical. If I only wanted to get it isothermal, then inerts would be good. But if I want to push it to being not, to cooling down, then I don't want inerts, because inerts will push it back to the vertical. I want it to move in this direction. So I want no inerts, or as little inerts as possible, and drastic cooling. Now how can I do drastic cooling? Let's think about ways of doing drastic cooling.
Once you're at the exothermic reaction, you see that when you add inerts to the exothermic, you're going vertical. So, okay, for the exothermic reaction, when you add inerts, you're shifting
The vertical isn't good enough here.
I know, so you want to go beyond that. But then, to get to the vertical, wouldn't adding inerts help you at that point, or?
Well, but how are you going to take the inerts out later? In fact, you don't want, but you don't want to get. Well, let me answer something. You don't want to for the first 10 minutes get to vertical and the next 10 minutes go beyond. What you want to do is go beyond immediately. As soon as it reaches the first maximum, you want it to go beyond. So you might say, well, to get it up to this maximum, I might want inerts, and to go beyond, I don't want inerts. But I can't take the inerts out later. So I would want to do the cooling, do it purely with cooling, because I know that later on I'm going to want to cool beyond the vertical. Because I can't put the inerts in for the first bit till I get to here and then take the inerts out. And then I need separators. Separators are generally not free. No such thing as a free, most, in real life people say there's no such thing as a free lunch. In chemical engineering there's no such thing as a free separation. Okay, so let's notice, we're going to talk about how to do the drastic cooling. Before I talk about doing the drastic cooling, let's think about these situations. In this situation, as the reaction proceeds, so XA goes up. As XA goes up, the rate goes, what's happening to the rate as XA goes up? The rate goes down. And the temperature is remaining constant. So no problem. As XA goes up, the rate goes down. What kind of reactor do I use? Plug. Because at for any given XA, I have the maximum rate I possibly can have. For any given XA, say this one, this value of XA, I'm at the maximum possible rate I can have. Because if I move to the right, I blow up the reactor. If I move to the left, I go to lower rates. So I use a plug here. Over here, as XA goes up, the rate goes down, as before. And also, in an endothermic reaction, as XA goes up, we don't follow this, we actually move a little to the left, the temperature goes down. And as the temperature goes down, the rate also goes down. So as XA goes up, the rate goes down. As XA goes up, the temperature goes down, and therefore the rate also goes down. So again, I have, in both of these, I have XA up implies rate down, and that implies plug. Here I have XA up implies rate down. It also implies T down, which also implies the rate down. And all this implies plug. Monotonic. Remember, monotonically decreasing rate with XA. On the other hand, the reversible exothermic, we can see that unless I do drastic cooling, then as XA goes up, the rate it heats up. So the heating up wants the rate to go up. So what would the rate be versus time? If I didn't worry that much about the details. Initially, I have a lot of reactant and a low temperature. So the reaction is moderately fast because of a high concentration of reactant, but it's a low temperature, so it's pretty slow. And remember, temperature is more important, it's exponential. So my rate starts out low. As I start reacting, I have a little less reactant, so the rate slows a little bit, but the temperature goes way up because it's exothermic. So what happens to the rate? Goes up. Well, this keeps going for a while, and eventually the temperature is high, but I have almost no reactants left. So what happens to the rate? It goes down. So the rate versus time, or if you like, Z in a plug flow reactor, or N for NCSTRs in series, the rate starts out low, it goes up, and comes down. So what type of reactor do we use when we have rate function that looks like this? Well, one choice is a recycle, or a CSTR plug flow in series. So one possibility, remember, that means 1 over the rate, looks something like this. So we could either use the recycle reactor, or a plug flow and a CSTR and a plug flow. or CSTR followed by a plug. Now, what we want to do here, though, is not simply use reactors. What we want to do here is use drastic cooling. So how would I do drastic cooling? Well, one method would be have reactors in series but have cooling between reactors. So what would that look like? If I do that, and I'm looking at T versus, say, Z here. In this reactor, if let's say I did plug flow, the temperature would go. So actually, let's see what we would like, what our goal is. Our goal here is for the temperature profile to look something like this. So this is the best we could have. That's what we were asking for, what we're looking for. And what would happen here is, when I go through the reactor, it started out at some temperature. When I go through the reactor, the temperature would increase. Then I get to the cooling regime. When I cool, am I plotting T versus Z? Okay, so I should actually look and see exactly, I'm mixing up plots. So T versus Z. What we would like for T versus Z is we'd like the temperature to, so as XA goes up, Z goes up. So we would like the temperature to go down. The temperature should be going down with Z. So I start at a high temperature, and I want the temperature to go down with Z. No, it's the other way around. Yeah, temperature should go down with Z. I start at a high temperature, and the temperature should go down as Z goes down, as I go along. So if I start at a high temperature, and as I move up in X, I'm moving forward in Z, the temperature should go down, moving to the left. So if I plot T versus Z, then I expect to start at a high temperature and to go down. Okay, so what happens here? Over here, I start out at some temperature, and as I go through the reactor, it heats up. But then I have cooling. The cooling cools me down, and then I enter the next reactor, and I go up again. And then I cool again. So, and that can continue. So this one curve is the goal, and this is the actual for this type of setup. So the actual isn't exactly the goal, but it's not terrible. Another possibility is if I have a reactor where I can bring in the inlet So this is the inlet. And what I could do is I could heat up the feed by contacting it with the reactor in a heat exchanger. And then as it moves through the reactor, I'm cooling the reaction mixture is being cooled by contacting with the feed. So what does that look like? So here's T versus Z. This is what I want. Okay. And let's notice what happens here. I start out at high Z. Actually, I want to use a different color here. So the actual, I'll use the pink. So I start out at high Z, start over there, and it's cool, and then it starts heating up. So the feed starts out here, and then it heats up as it contacts. And actually, it's got to enter the reactor. So it enters. And once it enters the reactor, it starts to heat up. Actually, let me make this a little different. And then once it enters the reactor, it starts to react. So it starts to heat up drastically, because here I've got lots of reactant. So it starts to go up. But then eventually, as XA peters out, the cooling from the contacting with the feed overcomes the heat being produced by the reaction. So it turns over and this starts to go down. That's the actual. So again, what I care about is the part of the curve that's in the reactor, not the part that's out. But this is fairly energy efficient in these green thinking times. Here I'm using the heat of reaction to heat up the feed. So and this curve isn't exactly this, but of course this is qualitative. Given your design, you could try to make these curves a little closer. Question? Okay, so, yeah.
So, if you have like a reaction going on, you have a situation where you have like,
Situation, yes.
you have a situation where there's a selectivity, right? If you have a.
Right, here we haven't spoken about selectivity at all, yet. We will, but.
But what I'm anticipating is that if you heat something up and then you cool it down drastically, you'll have problems with diffusion. And
With diffusion.
yeah, because if you want a certain product and you heat it up and you cool it down very drastically, you may not get exactly what it is that you're trying to get out of your reaction.
Can you be a bit more specific, because I'm not quite sure where you're going with the question.
So let's say you have A goes to B goes to C, right? And you want specifically B. And you heat it up, but then you cool it down drastically. You may wind up getting, as your end product, more C than what you desired.
Well, that all depends on the activation energies of the two reactions, which we'll talk about in detail in a little while. I don't know if we'll get to it today. Probably not. We'll probably talk about that at the next class, which is tomorrow.
So
This is
there
the
should be a,
kinetics du jour.
so there should be a
And
balance.
we'll talk about that in detail tomorrow.
Okay.
But you're talking about diffusion, which is not something that we've worried about here. And the reason, and that's why I'm sort of harping on this question, I would have just said selectivity we're doing tomorrow, because there's a point I want to make, is that if you remember, right now we made a number of assumptions when we began the semester. Single reactions, single reactors, ideal reactors, single phase. We've been taking away one assumption at a time, but we have not taken away, we've taken away single reactions, we've taken away single reactors. We have not taken away ideal reactors. In ideal reactors, diffusion is not an issue, because it's either well mixed, in which case diffusion, whether by diffusion or by stirring, it's well mixed. So it's infinitely well mixed. So infinity minus a little is still infinity, if you're worried about the diffusion. Or it's a plug flow reactor where there's zero diffusion. You can't get much less than zero when it comes to diffusion. So when you come to talk about ideal reactors, there's no discussion of a little less or a little less diffusion, because an ideal reactor, which doesn't really exist, but that's what we're dealing with, has diffusion's just not an issue. It's either zero or infinite. So changing it by 10% doesn't change zero, and by changing 0 by 10% doesn't change anything, and changing infinity by 10% doesn't change anything. But, so as not to be disappointed, we will talk about non-ideal reactors. We're just not up to it yet. But that's a coming attraction. Other questions? Okay, so again, I want to just go through the general procedure here. In the end, we use a design equation to design the reactor. But when I have a non-isothermal system, whether it's non-isothermal by virtue of the fact that the reaction has a non-zero heat of reaction, or by virtue of the fact that I'm adding and subtracting heat, or some combination of the two, then I need a connection between T and XA in order to use the design equation. If I can get that in closed form, as I did in this very simple lib balance, then I could plug in for T of XA and get RA as a function of XA and use the design equation. In more realistic cases,